Alright, in this video I'm going to show you how to model a shaft using ANSYS and find its natural frequency. For this I'm doing an example problem from Shigley's book, Shigley's machine design book. So first let's look at the statement of this problem. It says, consider simply supported steel shaft. As you see in this following figure, the diameter of the shaft is 1 inch and 31 inch is the length of the shaft. So it sits between two bearings. On the left bearing, okay, so and then two gears are sitting on this shaft. They weigh 35 pounds and 55 pounds. The first gear is sitting 7 inch to the left of the left bearing, 7 inch to the right of the left bearing. After that, we have another gear which is weighs 55 pounds and sits 20 inches from the left bearing and 11 inches from the right bearing. So we would like to find critical speeds of this shaft using ANSYS. Alright, so first let's look at this problem using Riley method. This example problem from chapter 7 of Shigley's book. Using Riley method finds the natural frequencies, part B. So let's look at the solution. So I'm not going to go through this solution here. So the natural frequency it finds is, first one is going to be 124.8 radian per second or 1192 RPM. So if you want to convert this to hertz, 124.8 divided by 2 and then divided by pi is going to give us the natural frequency in hertz. So it's going to be 1986 hertz. So so we would like to do this analysis and then compare our results with what this book reports by using Riley method. Alright, so let's see how we could do this. Alright, so I'm gonna do this using mechanical APDL, ANSYS APDL. So to do this, I opened this application already. So I go here, we have to do preferences, we select the structural modeling, and then pre-processing. To do pre-processing, we need to define element types. So I come here, and then I say, for the beam, for the shaft itself, we are going to use 2-node 188 beam element, and for the mass points, like the mass of the gears, we are going to use them. We are going to model them using mass points or mass 21 elements. So I added those two elements to our active library of active elements in our model. So we're going to use those guys. Okay, so let's close this. Alright, now we need to define those 2 point masses or the mass of those two gears. So to do that, I add real constant, I come here, add, and then those math elements, I okay that. So gear 1 is going to go under real constant set number 1. Its mass was 35 pounds. So I'm going to do this model in ANSYS system. 35 pounds is in kilogram. It's going to be like this, 0.453 almost, in kilograms. So this math is going to be effective in all directions. So I have to do this in all directions. 35.4 times this, 35 this, 35 this. So this is our first gear, second gear. So you see that mass was converted to kilograms. You can use ANSYS as calculator here. The other math is the gear weighs 55, so 0.453. So I need to do the same here. You can delete this and copy paste it. So Control C, and then I can do Control V. Oh, C. Oh, okay, that's okay. Let me type it. 55, 55, 5.453. Don't need forcing figures. Okay, so we have these for our second gear, the math of that. So I say okay. So we have set number 1, which is gonna be for gear number 1. Set 2 is gonna be gear number 2. So I close it. Next, I'm gonna define material property for the shaft. For the shaft itself, it's gonna be made of steel. So I go here. This guy, muscle elasticity of is 200 gigapascal, but I need to input that here in Pascal. So 200 giga means 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, Poisson ratio 0.3. I okay this. I'm gonna need density for natural frequencies. You know, if you're doing just a structural analysis, you don't need math, but if you're trying to find natural frequencies or model analysis, you're gonna need the math. Density of steel is 8,000 kilogram per cubic meter, so I okay this. Cancel. Oh, sorry. So let's do it again. 8,000. I okay. And you know, and this is material model 1. You put muscle elasticity and then density. I close it. Okay, so we have this. Next is section. Cross-section area of the beam element was, as you saw, was a solid shaft with a solid circle with a diameter of 1 inch. So I'm gonna change this to circular section. Radius is gonna be half an inch. Half an inch, every inch is like 25.4 millimeter. Then I divide this by 1,000. It's gonna give me my cross section, you know, radius in meter, which is what I want. All right, so we did this. Now we are gonna go to our next part is to model the shaft itself. So create, I'm gonna need to define key points. So key point 1, I'm gonna start the shaft from coordinate 0, 0, 0. That's where the left bearing is. Then the second key point is gonna be my left gear. It's gonna be key point 2, which is located 7 inches from to the right. So 7 inch times 25.4 divided by 1,000 is gonna give me that distance in meters. So this is gonna be key point 2, key point 3, which is the right gear. So it's gonna be what? 20 inches to the left. So key point number 3, key point number 4 is my right bearing, and it's gonna be at 31 inches from the left. So that's key point number 4. So let me change our view to isometric. Alright, so then I need to create line. So to show the shaft, so start from here to here. So this line is going to represent my shaft. Alright, so what else? Okay, so we did the modeling. Now for meshing, okay. So we have to go, if you remember, we have to assign attributes, you know, the properties of the sections we have defined. You know, the shaft has a diameter of 1 inch, so we have to state that, you know, indicate that to ANSYS that this shaft has that. And then those key points that we have gears sitting on that, we have to assign those gears to those points that I have here. All right, so let's go here. Alright, so all lines are gonna have beam number, that beam element. So I okay this. And then for key points, let's select this key point. This key point number 2. I'm gonna, if you remember, we said that key point number 2 is where the mass number 1 or gear number 1 is gonna sit. So I'm gonna say, here you see I selected that key point and I said mass element 21, real constant 1 is going to be assigned to point 2, and then I'm going to select point 3, and for that point 3 mass element, same mass element, but this time real constant 2, or that 55 pound of mass is going to go there. Alright, so we did we did the lines and we did that. Okay, so now size control. I'm gonna go and we just need one element per segment of this shaft. You don't need to have more elements. It doesn't hurt having more, but one is enough. Okay, so I'm gonna say all lines, I just need one element. So we see how it's going to show that here. So next, we're going to mesh it, right? So first I'm going to mesh key points. Select these 2 points. These 2 points. I'm going to mesh them. And then we need to mesh the lines. So pick all lines. We mesh that too. Alright, so we can now go list or take a look at our elements. Yeah, so you see I have math elements, 2 math elements, and then we have 3 structural elements, right, for the shaft. Alright, so next in modeling, you need to define loads or supports, right, boundary conditions. Alright, so I come here I'm gonna go apply displacement on key points. On the left bearing, I say okay. So that left one, it's not gonna move in X, Y, Z, so I'm gonna say 0. I'm gonna fix rotation, X, so it's like twisting, I'm gonna fix that too. But you can let the rotation Y and rotation Z to be free. Right, but I'm gonna fix the right side too, right bearing, and that's gonna prevent the shaft rotation or from rotation about y-axis or z-axis. So let's do it here, and then I'm gonna select this guy here. I say okay. So for this one, you can leave the X open and just fix Y and Z translation of motion there, okay, and say okay. So for modal analysis, we don't need to put forces. We define a core, structure, properties of structure, and then the boundary condition, and we just run the analysis. All right. So we are doing analysis type modal analysis. Let me okay that, and then analysis options. I like to see first hand frequency, number of modes to extract, and mode, and see number of mode shapes I want to extract. So say okay, and then it says in what range you want to find your natural frequency. I'm going to find the first 10 that are going to fall within the range 0 to 1000 hertz. Okay, and say okay. So now let's solve it. Hopefully we don't get any error. Alright, solution is done. So then you come here. Let me show you guys this example again. First natural frequency only is obtained here. which matters the most. So it is 124, and I showed you that in hertz, gonna be like 19 something. So, all right, let's come here, see what our analysis says. There you go. So we have our natural frequencies in hertz, as I said, 19.873. So 19.873 is very close to what we have here. So let me convert that for you. 19.873. As I said, if I multiply that by 2 and pi, you're going to get that in 124.86, which is very close to what Wiley says. Alright, so you see how it matches the results. Okay, we have first two natural frequencies are the same because the reason is this, because because this is a 3D shaft, so this can vibrate in XY plane. If you look at it here, you see here, it can vibrate XY plane, and it can vibrate in XZ plane. And in those two planes, natural frequencies are going to be the same. So as you see, first two are repeated, right? And first 1 and 2 are the same, 3 and 4 are the same, but then number 5 is not repeated. Probably that one is the one that is associated with twisting of the shaft. So we can take a look at them, and you can look at the videos. Let's see how we can see videos. How do I see the videos? Let's see. Our result here should go here. Alright, so first natural frequency, I'm gonna, degree of freedom solution. You can come here and say, just show me the entire displacement. And I'm gonna, if I click this, I say, okay, show me mode shape. And now, here it says how many frames you want to create. The more frame you make, it's going to be smoother. So let's see what we have is good. So the speed probably is not good. So let me change the speed. Okay, yeah. So if I increase the speed, okay, this is slowing down. Okay, so this is the first mode shape. Right? So, alright, let me stop this, and I'm going to move to the second mode shape. Second mode shape is going to be similar. As I said, it's going to be just in different plane, but just same thing, right? So let's see. Yeah, see? That first one was vibrating in XY, now it's vibrating in XZ. But the shape of the mode shape is the same. Alright, so now let's go see number 3. Okay. You know what? Let me generate more frames. Okay, so now let's look at this one. This is our, mode shape number 3. Mode shape number 3 and number 4 are going to be similar. As I said, one of them is going to be XY plane, the other one XZ. So let me move to this one. Now let me show you guys this. Yeah, as I said, you see that? It's just same shape, but it's just different plane. Number 5 was different. So my guess was that one is going to be the torsional one. So let's see what that was. I come here. Let's animate that too. Okay, so yeah, you see, no, this is actually axial. So that one, the chance of that getting excited is lower. Yeah, this is like axial, not the torsional one, right? So this one obviously is going to be just one. It's not going to be two of them, It's not repeated, because that's the only way axially this can get vibrated. Right, there is one way. Then let's look at the last one, the last mold shape. The last mold shape that we have extracted. See how that one is going to look like. Yeah, so the chance of this one getting excited, the higher ones, is going to be lower because there's going to be more energy in the system is required to get them excited. So let's look at it again, the result. So this first two are the most important one. Maybe the first two, when I say the first two, I mean 19.871 and then 94.1. That's maybe close to your operating natural frequency, operating frequency of the system. First one, when I convert it to radian per second or to RPM, okay, we have the RPM conversion here, let me show you that. First one, the RPM is 1200 revolution per minute. 1200 RPM is close to operating RPM of a lot of machinery, right? Electromotors or... So that's something we have to worry about. The second one, 94, is like almost 5 times, like 4 times. So that one is going to be like 5000 RPM. So that one is something you have to worry about too. So, but the ones after those, you see, are much higher, so we don't need to worry about those. Usually the first two are the ones that we need to worry about. All right? So I hope this helps. Now you saw how we model this shaft, using ANSYS. And if this model we made was for a shaft that has constant diameter, but if you have different diameters, different sections, the problem, is very similar. All you need to do is, when I was defining like beam sections here, I just define right now one section with that diameter, but you can define more diameters, more sections, and then just specify, give them different identification number here, and then when you're meshing, you can assign them to different sections of the shaft, and then you do your analysis. It's going to be very similar. So even if your shaft is more complex, you can do this approach like this here. All right, so yeah, so I hope you find it useful.